Welcome to Chemistry Solutions with Steve. This is a GCSE AQA Chemistry Higher Tier Paper 1 walkthrough, and it's from May 2024. You can download this paper from the AQA website, and you can complete it as a full marked exam under exam conditions, or you can use it for revision by pausing the video, going back, marking your work. Print it off or complete it on a device, the choice is yours. Please familiarise yourself with the front page of the exam. It contains a lot of information that will be helpful, and don't be complacent. I know you've seen it before. Anyway, let's crack on and good luck. Question 1. A student produced a salt by reacting copper carbonate with sulfuric acid. This is the method used. 1. Measure 50 cm³ of sulfuric acid into a beaker. 2. Add copper carbonate powder. 3. Stir the mixture. 4. Repeat 2 and 3 until the carbonate is in excess. Filter the mixture. 6. Warm the filtrate until crystals appear. 7. Leave the solution to cool and crystallize. 1.1. Complete the word equation for this reaction. And this is for 2 marks. So there are 3 products. We've been given carbon dioxide and we're looking for the missing 2 products. The key 2 bits in the reactants are the copper and the sulfuric, and we'll come back to those in a minute. You will recall that any carbonate reacts with any acid to form a salt, water and carbon dioxide. So at least one of those chemicals missing is water. We know that for a start. So to claim our first mark, we'll write water in the space provided. You will recall from your work on acids and bases and alkalis that when reacting an acid with an oxide or a metal carbonate, the metal forms the first part of the name of the salt. So in this context, copper carbonate will form a copper salt. And we know sulfuric acid always forms sulfates. Remember, it is sulfate, ATE on the end, not anything else. So, to claim our second mark, we write copper sulfate in the space provided, 1 mark for each, 2 marks. 1.2. Give one observation the student could make during step 4, which shows that the copper carbonate is in excess. So let's have a look at step 4. Here we are, copper carbonate in excess. So, what we'll find in the bottom of our container, our beaker, there'll be some powder, some copper carbonate powder that is unreacted. So to get your mark for this question, you write in the space provided there will be solid copper carbonate left in the solution, and you could also get a mark if you wrote that the fizzing had stopped, there was no fizzing. 1.3. Give one reason for filtering the mixture in step 5, and this is for 1 mark. Look at the previous answer. There's some solid left in the solution. To get clear solution for crystals, this solid must be removed. So, to claim 1 mark, write in the space provided, you would filter to remove any excess solid copper carbonate. 4. Name the equipment that can be used to warm the filtrate gently in step 6. And this is a 1 mark question. Now, to warm something gently to make crystals, a Bunsen burner is definitely not a thing you would use. It's out. So what you'd use is a water bath, which is a basin on a beaker of boiling water, or a specialised electric heater for 1 mark. 1.5. The maximum theoretical mass of the salt that could be produced using 50 cm³ of the sulfuric acid is 12.5 grams. The percentage yield of the salt is 92.8%. Calculate the mass of salt actually produced. Use the equation percentage yield is the mass of the salt actually produced divided by the maximum theoretical mass of salt that could be produced times 100, and this is for 3 marks. This equation is very wordy, so it's best if we sub in all of our numbers and all of our factors from the question and then rearrange the equation. Indicated here, the percentage yield is 92.8%. So we can sub that in. The maximum theoretical mass, that's in the purple colour, and that's 12.5 grams. So we end up with 92.8 equals the mass of salt actually made divided by 12.5 multiplied by 100. So to make the mass of salt produced the subject of the equation, we're going to multiply both sides by 12.5 and divide both sides by 100. And that way we end up with 12.5 times 92.8 divided by 100 equals the mass of the salt actually made. So if we crunch that on our calculators, that gives us a mass of 11.6 grams. So we'll get 1 mark for the equation, 1 mark for the rearranged equation, and 1 mark for the final answer, 3 marks. Now, if you're struggling with chemical calculations, I've produced several revision videos on different aspects of calculations, and there's a link for the one on percentage yield at the end of this video. Over the page, 1.6. Some salts can be produced by reacting sulfuric acid with a metal. Neither copper nor sodium is used to produce a salt with sulfuric acid. Give one reason why each metal is not used for 2 marks. Now we need to refer to the reactivity series, and we can see from here that sodium is quite high up in the reactivity series. So that means sodium is extremely reactive. Now if we look at copper, you'll see copper here is below hydrogen. So because copper is below hydrogen in the reactivity series, it will not react with the acid. And for sodium, the reaction of sodium is dangerous. So because of its high reactivity, you wouldn't react sodium because it's too dangerous, could explode. 2 marks. Over the page for question 2. This question is about the periodic table. Sodium and potassium are in group 1 of the periodic table. 2.1. Give one similarity and one difference between the electronic structures of sodium and potassium. And this is for 2 marks. So let's look at this little clip from the periodic table of elements. This is from the actual one that you will be supplied in your examination. And you can see sodium and potassium are there in group 1, circled in purple. If you can recall, elements that are in the same vertical group of the periodic table have the same number of electrons in their outermost shell or energy level. So that's a similarity. You will also remember that the periodic table is organised in rows we call periods, and they start with number 1 at the top for hydrogen, helium, and go down 1, 2, 3, 4. So sodium's in period 3 and potassium's in period 4. As we go down the group, each period has 1 extra energy level or shell. So in other words, sodium and potassium have different number of energy levels or shells. To claim our first mark for the similarity, sodium and potassium both have the same number of outer electrons. For the second mark for the difference, sodium and potassium have different number of shells. Sodium has 3, potassium has 4. 1 mark for each, 2 marks. 2.2. Give 2 observations made when potassium reacts with water, and this is for 2 marks. This is a very familiar reaction to you, and you should have seen this demonstrated by your teachers at least once in your chemistry career at school. You will see a very vigorous reaction, so you could see a mini explosion, you could see some fizzing, you'd see the potassium melting, the potassium floats, you should see a lilac flame. So any 2 of those for 2 marks. Question 2.3. So, potassium hydroxide solution is produced when potassium reacts with water. What is the colour of universal indicator when added to potassium hydroxide solution? Give 1 reason for 2 marks. Well, the colour of the indicator will be purple. And this is because we're dealing with an hydroxide. And a hydroxide, remember, is an alkaline. So the reason for the purple colour is the solution is alkaline. 1 mark for each for 2. Over the page, Table 1 shows the densities of some of the elements in Group 0 of the periodic table. You've got helium, neon, argon, krypton, xenon, radon. You've got a column that says atomic number and some densities in milligrams per cubic centimetre. Question 2.4. Plot the data from Table 1 on Figure 1. That's the graph below for 2 marks. So let's check our axes. We've got density up the Y, the vertical axis, and the atomic number is along the horizontal or x-axis. So let's zoom in on the scale and work out what each individual small gradation is. If we look at atomic number, if we look at this mark halfway between 0 and 20, that must be 10. 10. There are 5 marks in between 0 and 10, so therefore each smallest mark must be 2, 4, 6, 8, 10. Up the vertical scale, we've got 1 halfway between 0 and 2, and again there are 5 individual marks between 0 and 1, so each one of those must be 0.2. So let's look at plotting the graph. Remember, use a sharp pencil, a mechanical pencil works best, a ruler, and tick off each of the plots as you put them onto the graph so you know exactly where you're going with this. So the first plot is the atomic number 2 and the density 0.2. And then we just move it straight on, plotting each point as we go using your ruler. Although the question does not ask for a line of best fit, it is good practice to try and draw a line of best fit. So place your ruler and try and make sure your ruler goes through most of the points. If it doesn't, remember, try and leave as many points either side of the ruler so that you get what we might call a mean line. So your line of best fit, draw that with your pencil. And that's 2 marks. 1 mark for all the plots and 1 mark for the straight line. Page 2.5. Estimate the density X of krypton. Use figure 1 and table 1 for 1 mark. Here's table 1, and you can see this is what we're looking for. The best way to do that is use a ruler on your graph. Draw a line up like we've done here from 36. That is called a construction line. So we've gone across to 36, we're drawing a line up to touch the actual graph line, and then we draw a horizontal line with our ruler across over to the vertical, and we can see that that comes 3.2463.6 milligrams per centimetre cubed. So to claim our 1 mark for this question, we write 3.6. You could write C graph for working out if you wanted to, but as long as you've got that answer, 3.6, 1 mark. Question 2.6. The elements in group 7 are called the halogens. A more reactive halogen can displace a less reactive halogen from a solution of its salt. Which combination of solutions will produce a reaction when mixed? And this is for 1 mark. So if we look at the halogens, we've got fluorine, chlorine, bromine, iodine. Fluorine is the most reactive, and iodine at the bottom is the least reactive. So remind ourselves, a more reactive will displace a less reactive. In other words, there'll be a reaction. The first reaction between chlorine and potassium fluoride, well, chlorine is less reactive than fluorine, so it will not react. Second one, chlorine and potassium bromide. Chlorine is more reactive than bromine, so it will react, but let's look at the other ones to double check. Third one, bromine and potassium fluoride. Bromine is less reactive than fluorine, so will not react. And the final one, bromine and potassium chloride. Bromine is less reactive than chlorine. That will not react either, so the answer is the second choice, chlorine and potassium bromide for 1 mark. Question 2.7. Which of the following describes the trends going down group 7 for 1 mark? Now be careful with this because these all look very similar, so we'll look at how we can get through this. The relative molecular mass decreases and the boiling point decreases. The relative molecular mass decreases and the boiling point increases. The relative molecular mass increases and the boiling point decreases. The relative molecular mass increases and the boiling point increases. So let's go back to the halogens again. There they are, fluorine, chlorine, bromine, iodine. What do we know? You should recall from your work on the periodic table the trends in melting point and boiling point and molecular mass. As we go down the group, the molecules are getting heavier and heavier, so the molecular mass increases. Boiling point is connected to molecular mass because of those intermolecular forces. So the boiling point going down the group also increases. So we're looking in our answer grid. Both factors are increasing, and that's the fourth choice. So for 1 mark, we tick the fourth box. Relative molecular mass increases and boiling point increases. Over the page, question 3. This question is about models of the atom. Figure 2 shows 2 early models of the atom. On the left, you've got model A. You've got a circle and it says ball of positive charge. And then on the right-hand side, you've got model B. 3.1. Name the models of the atom shown in figure 2. So model A, we've got this ball of positive charge, and then within this positive charge we've got these little negative charges. Now this is reminiscent, and you will know from your work on the history of the atom that this is the plum pudding model. Plum pudding model. Now if we look at model B, this is more reminiscent of what we think of as the atom nowadays. You've got a central positive charge, and then you've got these radiuses, circles, almost like planets with these negative charges, which we assume are electrons, and this is what we call the nuclear model. So model A is the plum pudding model, model B the nuclear model. 1 mark each, 2 marks. 3.2. Compare model A with the model of the atom used today and use figure 2 for 4 marks. This is a levelled response with no specific marks allocated for different points made. Look at the description here. Level 2, scientifically relevant features are identified. The way in which they are similar, different is made clear, and that is the key to this, and some of magnitude of the similarity. There's a little bit of that. So let's have a look how we do that in order to get maximum marks. Now let's just look at this. This comes from the examiner's report on this question. Some of the best answers were written in the form of a table with comparisons such as no nucleus, has a nucleus. To score full marks, it was necessary to note a similarity as well as differences, with the most common similarity being both models have electrons. So I've clipped the model A from the previous question, previous part, and I've just copied here from the internet a picture of the modern atom. And let's have a look at the similarities. There are 2 mainly similarities. Both models contain electrons, they're negative charges. And both models have no overall charge either. So let's have a look at the differences, and these are numerous. The modern model has protons, model A doesn't. Modern model has a nucleus, model A doesn't. Modern model has neutrons, model A doesn't. The modern model is mainly empty space. Model A, the mass is spread out evenly, so in essence it is solid. And the mass in modern model is concentrated mostly in the nucleus. In the modern model, the electrons are in energy levels or shells, whereas in model A, the electrons are distributed randomly throughout the atom. Now you can see what we meant by a table. So we've got the plum pudding model and today, and down the left-hand side, the similarities and differences. It's quite acceptable to present this answer in this way. There's no need for all those sentences and full stops. So for the similarities, the plum pudding and the model of today both contain electrons, and both models, there's no overall charge on the atom. So the difference is the plum pudding has no nucleus, whereas the model of today has, and ditto, no protons and protons. The plum pudding model has no neutrons, the today model has neutrons. The plum pudding model has no empty space, and the model of today is mainly empty space. And finally, mass is evenly spread out in the plum pudding model, and in the model of today, the mass is concentrated in the nucleus. And for the final one, plum pudding model, in the plum pudding model, the electrons are spread around the model randomly, and in the model of today, the electrons exist in energy levels or shells. As was stated earlier, this is a levelled response. So it's not acceptable to think that you get a mark for every so many points made. Having said that, I think you need both the similarities, and then if you were to come up with 4 or 5 differences, I think that would suffice for your 4 marks. Over the page, 3.3. Chadwick's experiments showed the existence of neutrons in an atom. This led to an understanding of isotopes. Define the term isotopes and refer to subatomic particles in your answer. This is for 2 marks. I am sure this is one of those things that you've been told over and over again. You must learn your definitions, and they are in the glossary at the back or the front of your textbook. You can also find them online wherever you go for your online support. So it's a straight definition. Isotopes are atoms of an element with the same number of protons and electrons, but a different number of neutrons. 1 mark for the same number of protons, 1 mark for the different numbers of neutrons, 2 marks. Over the page, question 4. A student investigated the energy change of a reaction between zinc and copper sulfate solution. This is the method used. Measure 25 cm³ of copper sulfate solution into a polystyrene cup. Measure the temperature of the copper sulfate solution. Add 0.20 grams zinc powder to the copper sulfate solution. Stir the reaction mixture. Record the highest temperature reached. Repeat steps 1 to 5 with different masses of zinc powder. Figure 3, which is a graph, shows the results. So on the vertical or y-axis we have highest temperature reached in degrees Celsius. On the horizontal or x-axis we have the mass of zinc in grams. Question 4.1. Draw 2 lines of best fit on figure 3 and the lines should cross, and this is for 2 marks. So here you can see we're offering up our ruler and we're trying to get our ruler to line up with as many crosses as we can, and then with our sharp pencil we draw our smooth line of best fit. Then we look at the second set of crosses and we do the same. Notice there's an anomalous result. We can ignore that for now. And there we are, we've got our 2 lines and they cross. 1 mark for each line. Now, if the lines don't cross, then you lose a mark. So, 4.2, explain the results shown in figure 3. Do not refer to anomalous points. Use the data from figure 3, and this is for 4 marks. So, let's look at the first line of best fit. We can see it's a straight line. It's rising steeply from left to right. This tells us that the temperature is rising at a constant rate, and we've got to ask ourselves, because this is an explain question, why? Why? Because this reaction is exothermic. So, for our first 2 marks, we can write on the answer grid, in the first part of the graph on figure 3, the temperature rises steadily because the reaction is exothermic. Back to the graph and to the second line, the horizontal line. The horizontal line extends across to the vertical axis at 47 degrees. So where the points cross, where the 2 lines cross, this is telling us that the reaction has stopped because the temperature is no longer rising. Explanation, why is this? Well, this is probably because the copper sulfate has all been used up, because we can see that we're still adding zinc here, so the zinc must be in excess. So let's write all this out so we get our 4 marks. In the first part of the graph on figure 3, the temperature rises steadily because the reaction's exothermic. Underlined because it's an explain question. At 47 degrees or after 0.8 grams of zinc have been added, the reaction stops. This is because, again, the copper sulfate solution has been used up, and you could also say that the zinc is in excess. So 1 mark for saying the temperature rises and 1 mark for saying because it's exothermic. 1 mark for saying at 47 degrees or after 0.8 grams of zinc, and 1 mark for saying because the copper sulfate has been used up or zinc is in excess. 4 marks. Question 4.3. Explain why using a polystyrene cup gives more accurate results than using a glass beaker for 2 marks. This question is about insulation. A polystyrene cup is used because it is a better insulator. What does that mean? It means it prevents heat being lost, or as much heat being lost, to the surroundings, and it does it better than glass. It reduces the energy loss to the surroundings. It's an explain question, so to get our 2 marks, polystyrene is a better insulator than glass, therefore it reduces thermal energy loss to the surroundings. 2 marks, 1 mark for saying it's better, 1 mark for saying therefore. And 4.4. Complete the ionic equation for the reaction between zinc and copper sulfate solution. Include state symbols. So we've got zinc, solid, plus Cu2 plus aqueous goes to da-da-da-da-da-da. In brackets are the state symbols. So we've got to work those out as well as what the products are. So we know the zinc solid is going to lose 2 electrons and become a Zn2 plus ion. And the copper 2 plus ion is going to gain said 2 electrons to become a copper Cu solid. So for our first mark, we're going to write Cu bracket S for solid. And for our second mark, we're going to write Zn 2 plus brackets AQ for our second mark. It's 2 marks irrespective of which order you put them in. Over the page. A different student repeated steps 1 to 5 of the method 4 times using 0.50 grams of zinc powder. Table 2 shows the results, and here's table 2. You've got the highest temperature, and you've got 4 results there. 4.5. Calculate the mean highest temperature reached and include the uncertainty in your answer, and this is a 3-mark question. So in order to work out a mean average, we've got to add up the 4 results and then divide by 4. So we've got 37.6 plus 37.2 plus 37.8 plus 37.4 divided by 4. If we crunch all that into our calculator, what do we get? 37.5. So what about the uncertainty? Well, in this type of calculation, the uncertainty is the range of the results divided by 2. So we're looking for the highest and the lowest. So if we go up to the table, the highest result is 37.8 and the lowest is 37.2. So we work out the difference between those two, which is 0.6. Divide that by 2 and you end up with a uncertainty of 0.3. 1 mark for the mean average, 1 mark for the formula for uncertainty, and 1 mark for the final 0.3. .6. The results show random errors. The student did not make any measuring errors. Suggest one reason for the random errors in this experiment for 1 mark. Well, there's quite a few you could have here. So what are we looking at? We're looking at the temperature. So the temperature could have been different at the start. So that would give you a different higher temperature. Also, there's the stirring could be inconsistent. You might stir one particular experiment but not the other, and you might leave the lid on or the lid off. So for any one of these 3, the starting temperature could be different each time. The student could have forgotten to stir the reaction, or the lid of the polystyrene cup could have been left off in one of those experiments. 1 mark. Over the page. This question is about ionic compounds and electrolysis. Calcium chloride is an ionic compound. 5.1. Calcium and chlorine react to produce calcium chloride. Describe what happens to calcium atoms and chlorine atoms when the ionic compound calcium chloride is formed. This is for 4 marks. Let's take a look at a diagram. You'll have recognised this diagram from school lessons on ionic bonding. We've got a calcium atom here. It's electronic configuration 2882, and in its outer shell it has 2 electrons. Now if we look at the 2 chlorine atoms, their configuration are 287, so they've got 7 electrons in their outer shell. So calcium needs to lose those 2 electrons, and each of these chlorines needs to gain an electron, and then both of these species will have a full outer shell. Remember the octet rule. So in effect what happens is the calcium atoms donates its 2 electrons, 1 each, to the 2 chlorine atoms. Now if you look at the next diagram, the calcium atom then becomes a Ca2+ ion with an electronic configuration 288. Because it's lost 2 electrons, it's got 2 residual plus charges. Each one of those chlorines, they've gained an electron, so each one of those has a minus charge, -1. So we have 2 Cl1 minuses. So let's put this into an answer that was going to get us 4 marks. A calcium atom will lose or transfer its 2 outer electrons. 2 chlorine atoms will each gain 1 electron. This means that 1 calcium atom will react with 2 chlorine atoms. 1 calcium Ca2+ ion is formed, and 2 chloride Cl1- ions are formed. 1 mark for saying that the calcium loses 2 electrons. 2nd mark for the 2 chlorine atoms each gaining 1 electron. 3rd mark for stating that 1 calcium atom reacts with 2 chlorines. And the 4th mark for saying that the Ca2+ ion and 2 Cl1- ions are formed. 4 marks. Question 5.2. Solid calcium chloride cannot be electrolyzed. Give 1 reason why for 1 mark. Solid calcium chloride exists in what we call an ionic or ionic crystal lattice, and it is a diagram of one. And we can see these ions, they're fixed in place and they cannot move. If they cannot move, they cannot carry the charge, therefore they cannot be electrolyzed. So to get 1 mark, we write in the space provided, the ions cannot move. 5.3. Name the product formed at the negative electrode when aqueous calcium chloride solution is electrolyzed, and this is for 1 mark. So if we're looking for a product at the negative electrode, a positive ion must be attracted to the negative electrode in order to be discharged. 2 positive ions present in calcium chloride solution are calcium, Ca2+, and hydrogen, H+. Now in this context, hydrogen, because it's lower in the reactivity series, is discharged in preference. So to get 1 mark for this question, we write hydrogen in the space provided. Point 4. Over the page. What is the half equation for the reaction at the positive electrode when aqueous calcium chloride solution is electrolyzed? Tick 1 box for 1 mark. So we've got 2Cl- goes to Cl2 plus 2E minus. Cl2 plus 2E- goes to 2Cl-. 4OH- goes to O2 plus 2H2O plus 4E-. O2 plus 2H2O plus 4E- goes to 4OH-. So this time we're looking for a reaction at the positive electrode. So negative ions must be attracted to the positive electrode and give up their electrons. If we look at the first one, 2Cl- is a negative, so that's okay. The next one, Cl2, is not a negative ion. The next one, 4OH- is a negative ion, so that's a possibility. And the 4th one, O2, and H2O, no negative ions there. So it's only the first and the third one. But in the solution, there are two minus ions. There are two negative ions, Cl1 minus, OH minus. But let's remember, when we've got chloride ions in solution, chloride ions are always discharged in preference to OH minus. So the answer must be the first choice. 2Cl minus goes to Cl2 plus 2 electrons. So to get 1 mark for this question, tick the first box. Over the page, 5.5, a student investigated the electrolysis of green copper chromate solution. Figure 4 shows the apparatus. Got this figure 4 here. You've got a power supply, which will be batteries or a power bank. You've got a piece of filter paper soaked in an electrolytic solution, a drop of green copper chromate solution in the middle, and then on the left a negative electrode, on the right a positive electrode. Figure 5 shows the results. So here's figure 5. You've the same outline, but in the middle of this filter paper now, on the left we've got a blue colour, and on the right central we have a yellow colour. So what was there in the first place is now separated into blue on the left and yellow on the right. Copper chromate solution contains the ions Cu2+ and CrO4 2-. Explain the results shown in figure 5, and this is for 3 marks. If we go back up to figure 5, we can see the blue colour is a result of something moving towards a negative electrode. So that must be a positive ion, must it not? And we've got 2 ions, and the positive ion is the Cu2+. And you may have known that Cu2+ ions are in fact blue, hence the blue of copper sulfate solution. So by deduction, the yellow colour moving to the right towards the positive must be a negative ion. And in the question it says CrO4 2-. And indeed, chromate ions are in fact yellow. So the yellow colour is a result of the chromate ions. So let's put this into something sensible to get our 3 marks. Copper 2 Cu2+ ions are blue and are attracted and therefore move to the negative electrode. Chromate ions CrO4 2- must be yellow and are attracted and therefore move to the positive electrode. In terms of marks, the fact that you've deduced that the copper ions are blue and the chromate are yellow is 1 mark. And then you've got a 2nd mark for the copper ions moving to the negative electrode, and the 3rd mark for the chromate ions moving to the positive electrode. 3 marks. Over the page, a student investigated the voltage produced by a different pair of metal electrodes in a chemical cell. Figure 6 shows the apparatus. You've got voltmeter, a nickel electrode, electrode A, and a 1.0 moles per decimeter cube sodium chloride solution, which is our electrolyte. So this is the method used. Place a nickel electrode and an electrode made from a different metal, electrode A, in a 1 mole per litre decimeter cubed sodium chloride solution. Measure the voltage produced. Repeat using different metals for electrode A. And table 3 shows the results. And you've got copper, Cu minus 0.59 in volts, magnesium, nickel, silver, and zinc. And you can see those values there. So what's it asking us? 6.1. Write the symbols of the 5 metals in table 3 in order of reactivity and justify your answer for 3 marks. So we've got the most reactive to the least reactive, and then at the bottom the justification. So let's go back to the table. This is all about the maximum positive voltage. The metal with the largest voltage is the most reactive. So that's magnesium. The next one down then would be zinc 0.51. Third, nickel at 0. And then copper minus 0.59. Silver minus 1.05. So putting those into order, we've got them here: magnesium, zinc, nickel, copper, silver. 2 marks for that one. Now the justification, we've already alluded to this. We said that the most positive voltage, the highest possible positive voltage, is the most reactive. And so that's really what we need to write. The metal with the highest positive voltage is the most reactive. And that's your third mark. So if we look down at the answer grid, we'll see what we're going to write down to get our third mark. So the higher the positive voltage, the more reactive the metal, 3 marks. 6.2. The voltage produced by a chemical cell depends on the concentration of the electrolyte solution. Plan an experiment to investigate how the voltage produced by a chemical cell varies with the concentration of the electrolyte. The following substances are available. The metal electrodes in table 3, a 1.0 mole per decimeter cube sodium chloride solution, and pure water, and this is for 6 marks. Now this is a level marked answer, so it's one of our 6 markers, but it's not on a required practical. This is where you should be using some of those required practical skills. So in order to get 6 marks or 5, so you need to get to level 3, and the method would lead to production of a valid outcome, and that means controlling variables, key steps identified, so you need to get everything in, and logically sequenced in the right order. So we're going to use the apparatus from figure 3, and the metal electrodes that we'll use are the nickel one and magnesium. We can use any as long as there's a difference in their reactivity, and you can see the diagram there. So what we're going to do now is just put that into a few simple sentences. So use the same apparatus as in figure 3 using a nickel electrode and a magnesium electrode. Add 20 cm cubed of a 1.0 mole per decimeter cube sodium chloride solution to the beaker. Attach the voltmeter and measure the voltage. Record the voltage. The question is asking us to investigate concentration, so we need to change the concentration of the sodium chloride. We need to use the same electrodes and the same total volume of solution. So what we're going to do is we're going to take half the solution, so we're going to measure with the measuring cylinder 10 cm cubed of the solution, discard the other 10, and then add 10 centimeters cubed of distilled water, and this will dilute the concentration. And if we continue doing this each time, the concentration will halve each time, and we get 5 concentrations, which is a great range of results. To put this into our sentences, to change the concentration, measure with the measuring cylinder 10 cm cubed of the NaCl solution and add 10 centimeters cubed distilled water. Record the voltage, repeat the dilution until 5 different concentrations have been used. In order to ensure valid results, use the same 2 metals and the same volume of sodium chloride solution. 6 marks back of the net. Over the page, 6.3. Describe how a hydrogen fuel cell produces a potential difference for 2 marks. So let's look at this diagram. This is a simplified diagram of a hydrogen fuel cell. You've got hydrogen going in one side, and what happens in this side is the hydrogen is oxidized. In other words, it loses electrons. On the other side, you've got oxygen going in, and this picks up those electrons. And in essence, what we get coming out the end is water. So the hydrogen reacts, so the hydrogen is oxidized. And here's a simplified equation of that. Oil rig, remember that. Oxidation is loss of electrons, and this creates the flow of electrons, the potential difference. And then the oxygen's involved by being reduced, picking up those electrons. And again, a simplified equation of the reaction producing water. So, in other words, to get 2 marks, hydrogen is oxidized in a fuel cell to produce a potential difference. The reaction with oxygen produces water. So 1 mark for saying the hydrogen is oxidized, 1 mark for saying that the reaction produces water. 2 marks. For the page, question 7. This question is about iron. 7.1. Iron is a metal. Describe how iron conducts thermal energy, and this is for 2 marks. This is all about metallic bonding, and you've seen this diagram loads of times before, I'm sure. This is a typical model of what metallic bonding is like. We've got these positive ions in a sea of delocalized electrons, and these delocalized electrons were able to transfer the thermal energy through the metal. So, to get our 2 marks, metals contain a sea of delocalized electrons which allow the transfer of thermal energy through the metal. 1 mark for the delocalized electrons, 1 mark for transfer, 2 marks back of the net. 7.2. Pure iron is too soft for many uses. Explain why mixing iron with other metals makes alloys which are harder than the pure iron for 3 marks. So again, let's look at a diagram of what this looks like. Here on the left we've got a pure metal where we've got all the atoms the same and they're all in layers and they can bend and stretch as those layers slide and slip past each other. On the right hand side, in an alloy we stick in an atom that's a slightly different size, could be bigger, smaller, and now the layers can't slide. The different size atoms prevent the layers sliding over each other. So to get our 3 marks, in an alloy there are different sized atoms, 1 mark. These disrupt the layers of atoms, so make them distorted. The layers of atoms are now less inclined to slide over each other. So for marks, 1 mark for different sized atoms, 1 mark for distorted layers, 1 mark for not able to slide. 3 marks. 7.3. When iron reacts with chlorine, 0.12 mol of iron reacts with 0.18 mol of chlorine Cl2. Which is the correct equation for the reaction? Tick 1 box for 1 mark. This is all about mole ratios. So we've got 0.12 moles in a ratio with 0.18 moles. So if we write out the ratio here, we can't have fractions and decimals of ratios. We need whole numbers. So to get whole numbers, we divide both sides by the smallest number. So 0.12 divided by 0.12 is 1. And then 0.18 divided by 0.12 is 1.5. Now that's still no good because we've got 1.5. So a simple trick here is double both sides. So if we double both sides, the ratio now becomes 2 to 3, iron to chlorine. So if we go down our list and find out which one it is, not the first one, it's not the second one. Look at this here, the last one, 2Fe plus 3Cl2, that's our answer. Tick in the box, 1 mark. The most common oxides of iron are Fe2O3 and Fe3O4. 7.4. What is the ratio of the numbers of ions in Fe3O4? For 1 mark, tick 1 box. Now we know an oxide ion is O2 minus. So in Fe3O4, there must be 4 O2 minuses. So altogether there must be 8 negative charges. Now we know a compound like Fe3O4 can have no overall charge. So there must be 8 positive charges. All of our answers include 4 O2 minuses. So let's find the ions. So if we look at the first one, 2 Fe2 plus 1 Fe3 plus, that gives us 7 positives, no good. Next one, 1, 2 plus, 2, 3 plus, so that's 1, 2 plus 6, that makes 8. That could be our 1. If we look at the next one, 3 times 2 plus, that makes 6. That's not right. And then the last one, 3 times 3 plus, that makes 9. So it's the second choice. So 1 tick in the box for the second choice for 1 mark. Over the page, 7.5. Calculate the percentage by mass of iron in Fe3O4. Relative atomic mass is for oxygen 16, iron is 56, and this is for 3 marks. The brief formula for the percentage composition is the mass of the element divided by the mass of the total compound times 100. So the mass of the element is iron, and in Fe3O4 there are 3 atoms of iron. The mass of the compound is the total mass of Fe3O4. So the mass of iron for the top is 3 times 56. The mass of the compound is 3 times 56 plus 4 times 16. Fe3O4, 3 ions, for oxygens. So if we follow this through, that comes to 168 divided by 168 plus 64, 8 divided by 232 times 100, and that comes out at 72.4%. You're awarded 1 mark for working out the relative formula mass of the iron oxide, 1 mark for the calculation 168 divided by 32 times 100, and 1 mark for your final answer, 3 marks. 7.6. Fe2O3 reacts with carbon to produce carbon dioxide. The equation for the reaction is 2Fe2O3 plus 3C goes to 4Fe plus 3CO2. Calculate the volume of carbon dioxide gas at room temperature and pressure that is produced from 40 kilograms of Fe2O3 using excess carbon. The MR for Fe2O3 is 160 and the volume of 1 mole of any gas at room temperature and pressure is 24 decimeters cubed, and this is for 5 marks. So this is what we might call a mixed equations, mixed calculations, where we need different formulas. And so what we need to do is do it step by step. So step 1 is often, most cases, moles of the known, right? So we use our formula triangle with Mr. Moles with his mass on his head, but we need to have our mass in grams. So 40 kilograms, remember a kilogram is 1,000 grams, so 40 kilograms of Fe2O3 equates to 40,000 grams of Fe2O3. So now we've got our mass, we use Mr. Moles with the mass on his head, and then we're going to use the moles is the mass divided by the Mr. So the moles is 40,000 divided by 160. 250 moles of Fe2O3. So step 2, let's look at the mole ratio. We go to the equation for the mole ratio, and we're looking at the mole ratio is 2 to 3. Now we use the mole ratio to work out the moles of the unknown. So if we've got 250 moles of Fe2O3, the moles of CO2 is going to be 250 multiplied by 3 divided by 2, because that is the mole ratio, 3/2. And when we crunch this on our calculator, that gives us 375 moles of CO2. Step 3, moles to vols, moles to volume. And again, there's another formula triangle here. And this is quite simple. The volume of any gas is the moles times 24. And it says above, doesn't it? The volume of 1 mole of any gas, room temperature pressure, is 24 dm3, decimeters cubed. So if we've got 375 moles, to get the volume of carbon dioxide, we must multiply 375 by 24, and that gives us 9,000 decimeters cubed. Now it's important that we look at mark allocation. We get 1 mark for converting kilograms to grams, 1 mark for the moles of Fe2O3, 1 mark for working out the moles of CO2 using the molar ratio, 1 mark for the sum 375 times 24, and the final 5th mark goes to our final answer, 9,000 decimeters cubed. Over the page, question 8. This question is about propane, C3H8. Figure 7 shows the displayed structural formula of propane, and you can see it displayed there, figure 7. 8.1. Explain why propane has a low boiling point, for 3 marks. Now there are 3 key points here, and the first one is that propane is a small molecule. Between the molecules there are weak intermolecular forces. That is an important phrase. Learn it. Weak intermolecular forces. And these weak intermolecular forces are easy to overcome. So let's construct an answer. Propane is a small molecule. This means, and I've underlined that because this is our explain bit, this is our connector. This means there will be weak intermolecular forces between the molecules. These forces will require less energy to overcome them. So the marks are allocated. Propane is a small molecule, 1 mark. This means there'll be weak intermolecular forces, 2 marks. These forces require less energy, 3rd mark. Back of the net, 3 marks. For the page. Propane reacts with oxygen to produce carbon dioxide and water. The reaction is exothermic. 8.2. Figure 8 shows 4 reaction profiles. And here they are. You've got A, B, C and D. Look at them closely. You can see they're all familiar. You should have seen these many times in your chemistry lessons. Which is the correct profile and labels for the reaction between propane and oxygen? Tick 1 box for 1 mark. So let's go back up to the stem of the question. The important bit here is the reaction is exothermic, and exothermics have a particular reaction profile that looks like this. So that immediately rules out C and D. So it must be either one of A or B. So let's look for the labels. In A, the overall energy change is actually incorrect. It's the one in B that's the correct overall energy change. We tick box B for 1 mark. Over the page, 8.3. Figure 9 shows the displayed formula equation for the reaction between propane and oxygen. And you've got these structural formulas here, so we're going to use those in a minute. The overall energy change of this exothermic reaction is 2219 kJ kilojoules per mole. Table 4 shows the bond energies of the bonds in this reaction. And we'll use these also in a moment. Calculate the bond energy of the CH bond X shown in the table there. And this is a 5-mark question. So the bonds on the left-hand side, the reactant bonds, we have to count them because we need to know how many there are. So we just go through and tick each one and add it up, and we can see that there are 8 CH bonds, okay? And these are the bonds known as X. And we can also see that there are 2 carbon-carbon bonds, 2 CC bonds. Over towards the oxygens, well, that's quite easy. There are 5 OOO. Double bond oxygens, 5 of those. So in order to complete this task, what we're going to do is I'm going to suggest you draw a table like this. And on the left hand side, you put the bonds broken. On the right hand side, the bonds made. So we can see here that we've got 2 carbon-carbon bonds. So we look in the table, carbon-carbon bond is 347. So we've got 2 times 347. When you total add up, that comes to 694. We've got 5 OOO bonds, 5 oxygen double bonds. So in the table, oxygen double bond 498. So 5 times 498, crunch that on your calculator, 2490. And don't forget, we have to add our 8 X's, our 8 CH bonds. So if we look at our products, these are where we find the bonds made. Carbon dioxide, CO2, there are 2 COO bonds, and there are 3 molecules. So altogether we've got 3 times 2, 6 COO bonds. Likewise with the water, we've got 2 HO bonds in H2O, and there are 4 molecules. So 4 2s, 8 HO bonds. So we transfer this to the table. 6 times COO equals 6 times 805, because that's from the table. The 805 is the COO bond. That gives you 4,830. And then the 8 OH bonds, each OH bond is 464. So 8 times 464, 3,712. And what we do now is we add up both sides. On the left, we have 3184 kilojoules per mole plus 8x. On the right-hand side, we have 8,542 kilojoule moles. Now, we use the equation. The overall energy change is the energy from bonds broken, take away minus the energy from the bonds made. Now, if we go back up into the question, we've been given the overall energy change. And that is 2219. But look, it's an exothermic reaction. So that energy change must have a negative value because it's an exothermic reaction. And this is a place where lots of students will make a little mistake. So don't forget, exothermic reactions have a negative energy value. So if we sub all that in, minus 2219 equals, in brackets, 3184 plus 8x minus 8542. So through a bit of algebra, we move our 8542 over to the other side. That becomes plus. And then we move our 3184 over to the left-hand side. That becomes minus. So that leaves us 8542 minus 2219 minus 3184 equals 8x. So if we evaluate that 8x is 3139, so x is 3139 divided by 8, so that comes out on your calculator at 392.375. We look at the other values, they're all in 3 sig figs, so we're going to write 392 for our answer. Now a mark. 1 mark for the total value for the bonds broken, 1 mark for the bonds made, 1 mark for the equation to show energy change, 1 mark for 8x equals 3139, and 1 more mark for your final answer, 392. 5 marks. Over the page, question 9. This question is about acids and their reactions. Acids can be either weak or strong. 9.1. What is meant by a weak acid? And this is for 2 marks. If you remember, acids are all about hydrogen ions. Acids provide hydrogen ions. And the more ions they provide, the stronger they are. So acids that are weak are only partially providing these hydrogen ions. And we say this is partially ionizing or partially dissociating. And this, of course, has to be in solution, in an aqueous solution with water. So 1 mark for saying partially ionizing and 1 mark for saying in solution with water. 9.2. Explain what happens to the pH of an acid as the acid is diluted with water for 2 marks. Now, again, this is about hydrogen ions, and the pH will go up. In other words, the numbers will get higher if the concentration of the hydrogen ions gets lower or goes down. So the pH of an acid will go up or rise because, and it's an explain, so because the concentration of the H plus ions is getting smaller, or we can say decreasing. 1 mark for saying the pH of the acid will rise, and the 2nd mark for saying because the concentration of H plus ions is decreasing. Over the page, 9.3. A student does a titration to find the volume of acid needed to neutralize an alkali. The student fills a burette with the acid. Give 3 more steps the student must do before adding the acid to the alkali from the burette. And you should name any equipment used, and this is for 3 marks. You must say that you would use a pipette to dispense and measure the alkali. That must be a case. And there's about 3 or 4 more things you could say. You put the alkali into a conical flask, you use an indicator such as phenolphthalein, you could put it on a white tile to show the colour changes in a better contrast, or finally you could take the initial burette reading before starting the titration. So let's look at a construction of an answer. As we've said, we must measure the volume of the alkali in a pipette. And then we've got 3 more choices. Place the alkali into a conical flask, add a suitable indicator such as phenolphthalein, and then a couple more that I've put at the end. You could use a white tile and record the initial burette reading. So 1 mark for each of the above, but as we repeat for the final time, the first one is a gimme, and any 2 from the last 4. 3 marks. 9.4. The student titrated a solution containing 0.0045 moles of sodium hydroxide with a 0.15 moles per decimeter cubed hydrochloric acid. The equation for the reaction is NaOH plus HCl goes to NaCl plus H2O. Calculate the volume of hydrochloric acid in centimeters cubed needed in the titration. This is for 2 marks. At first, this looks like a complicated but different titration calculation, but in actual fact, it's a lot easier than it looks. First thing to know, it's a 1-to-1 ratio, and it's all about the moles. Look at the equation. 1 mole of NaOH reacts with 1 mole of HCl. Therefore, 0.0045 moles of sodium hydroxide will require 0.0045 moles of hydrochloric acid to neutralize it in this reaction. So we can write this down. 0.0045 moles of HCl react with 0.0045 moles NaOH. Now we have the moles of hydrochloric acid, we have the concentration of hydrochloric acid, so we use our formula triangle NCV to work out the volume. NCV standing for, of course, number of moles, concentration and volume. Not forgetting that our volume in our concentration is decimeters cubed and in our titration is centimeters cubed, so we must divide our V by 1000. So as we sub into our equation, the concentration here in yellow, 0.15, number of moles 0.045. So we can write the expression volume equals N divided by C, the number of moles divided by the concentration. So that equates to 0.0045 divided by 0.15. And that equals 0.03 decimeters cubed. And the volume must be in centimeters cubed, so we multiply that by 1000. 1000 times 0.03 gives 30.0 centimeters cubed. 1 mark for working out the moles of hydrochloric acid needed, and 1 mark for your NCV, giving you your 30. 2 marks. That was a toughie. 9.5. A calcium atom is larger than a magnesium atom. Explain why calcium reacts more vigorously than magnesium with hydrochloric acid of the same concentration. This is for 3 marks. The electronic structure of magnesium is 282, but calcium is 2882. So you can see it's got an extra shell. So its outer electrons are going to be further away from the nucleus. This means they'll be less strongly attracted to the nucleus because of that extra distance. The less attracted electrons are towards the nucleus, the more easily they're lost. So let's put this into an answer that's going to get us 3 marks. Calcium has 1 more outer electron shell than magnesium. Therefore, its outer electrons are further away from the nucleus. This means the electrons are less attracted to the nucleus and more easily lost. Notice the underlinings are those connecting words that get us the explain marks. 1 mark for saying that the electrons are further away, 1 mark for saying they're less attracted, and a 3rd mark for saying that they are more easily lost. 3 marks. Well, that's the end of this video. If you've got to this point, thanks for sticking with it. There are more videos like this at the end. You'll see there. You know what to do. Like me, subscribe,